Okay, so today what we're going to do is look at a lot of specific cases for the coupled wave analysis for the, in this case, the approximate coupled wave analysis that are normally encountered. And I've had to deal with most all of these different situations. And again, this model that we're developing is going to be very, it's quite versatile in handling these different cases. Yes?
So just to confirm, sorry, for logistics for the class, we have homework due on Thursday and lab next week, it looked like?
So there is we have lab 4. I'll go over it on Thursday. But lab 4 is going to be next week, the 16th and 17th of November. And I forget what due date I had for
Thursday the 12th is what it says.
for homework 5. We could probably have homework due next Tuesday. I think that would be a little better. So homework 5 we'll have on the due on the 17th. Yeah, I think there's one more homework assignment, but yeah, I should go through pretty much everything that you need for homework 5. I'll have another look at it and see. I may push that back to Thursday after looking at it, but it depends on how much I cover today. Thanks for bringing that up. Okay, so the basic coupled wave equations that we were working with or derived have the following form. We reduce them to kind of a single derivative expressions where we have this c sub r, which is cosine of our angle of incidence, times the derivative with respect to z of the reconstruction field plus the average absorption times r equals minus j times the coupling coefficient times s. So this has the coupling, again, between the reconstruction beam and the signal beam. And then we have c sub s, which is the cosine of the angle of the diffracted beam, times s prime plus alpha plus, j times the detuning parameter, Greek j, times s is equal to minus j kappa times r. So these are this is the pair of coupled wave equations that we are going to be solving throughout. And again, so the nature of this is that the coupling occurs, as you can see here, between the two different fields through this coefficient, which is going to relate either to an index modulation or a absorption modulation of the medium, or a combination. We could have a mixed grating where we have both types of gratings occurring, both absorption modulation and refractive index modulation occurring. And the tuning parameter, again, this is this beta squared minus sigma squared over 2 beta, where beta, again, is just the average propagation constant, 2 pi n over lambda, gives us kind of this sense of the selectivity. So this will tell us, again, this is what we call a detuning, and it's detuning from the Bragg condition. All right, and so when we have the efficiency of our grating, we're going to have something that looks like that for the diffraction efficiency, where this is, say, the Bragg angle or the Bragg wavelength. And again, there's going to be some bandwidth, and what we'll be doing now is determining the functional form for this diffraction efficiency. And again, so a simpler form for this, if we only have small perturbations or small detuning, detuning from the Bragg condition, we can put this in a more intuitive or useful form, easier to use form, I should say, of delta theta times the magnitude of the grading vector sine of the angle of the grading vector minus theta 0 minus delta lambda k squared over 4 pi n, where, again, so we have theta is equal to theta 0 plus delta theta, and lambda is equal to lambda 0 plus some delta lambda deviation from the Bragg condition. So with that, we can kind of have a sense of how things are changing, how selective, how broad, how, what the shape of that is to some degree with variation from the Bragg condition, okay? As we'll see in all these cases too, when, by eliminating this particular term, this detuning term, which means then we're at the Bragg condition, we can get a really very intuitive form for the diffraction efficiency expressions. And so we'll have a look at those as well. So what we were considering then is, how to solve these. And so for the reconstruction field that we have, R of z, that was equal to R1 e, I'm sorry, just e to the gamma 1 z plus R2 e to the gamma 2 z. Since, again, these are first order differential equations, and R1 and R2 are constants, and we have a similar case for the diffraction field, S1 e to the gamma 1 z plus S2 e to the gamma 2 z. So these are the fields, and the total field inside the medium, E of z, is just equal to this R of z e to the minus j k dot r, I'm sorry, rho dot r, plus S of z e to the minus j sigma dot r, right? So again, so those are the amplitudes of the two fields that we have that that we're after in order to determine the diffraction efficiency. Okay, and so in solving this, our steps in solving this are to solve for what these constants are. So we have R1, R2, S1, S2, and gamma 1, gamma 2. So we saw that by manipulating these equations, these two equations here, what we can get are the values for gamma 1 and gamma 2 in terms of the parameters for the material, the hologram, and the material associated with that hologram, which is 1/2 times alpha over CR plus alpha over CS plus J times the tuning parameter over C sub S, plus or minus 1/2 times alpha over CR minus alpha over C sub S minus J times the detuning parameter over C sub S, that quantity squared, minus 4 times kappa squared over C sub R C sub S. Okay, so that is these coefficients that we were able to get straight away. And the other coefficients that we need are R1, R2, S1, S2. And so those we get from the boundary conditions. And we were kind of working our way through those. Again, so my first 15 minutes is a very quick summary of what we went through. We went through a lot of stuff last week, so this is the little synopsis here. So for the transmission grading, again, we have something that looks like this, where for a unslanted transmission grading, and again, so the problem comes about in the approximate coupled wave model is that we have to choose whether the grading is a transmission or reflection. So we have to answer that because the solution that we get is going to be based on the boundary conditions for the either the transmission or the reflection hologram. Later, I'll briefly go through some of the parts of the rigorous coupled wave. We don't have to make that distinction in that case. The boundary matching conditions are very general, but the coupled wave equations are much more complicated. They are second-order derivative equations instead of first, and it really complicates the problem, but it gives you a lot more generality in the solution. So there will be cases where you need to use a rigorous coupled wave model. Fortunately, now there are a number of simulation packages that are commercially available, but it's not too difficult to go through an algorithm to actually generate that. I think in that book chapter on coupled wave analysis that I gave you, at the end of that, there's an algorithm actually, so you can actually set up kind of a rigorous coupled wave if you need to. So it's nice to have your own program, I find, so you could tailor it to what you need. And you'll have the tools to do that after we discuss that. Okay, so again, so for the transmission hologram, we have, again, so here is z equals 0 and z equals d, and we have our reconstruction field here, r of z, and then we have possibly some r left at at z equals d, and we'll also have the signal beam strength. That's where it is measured. And so we would find that, at the front end we have a value for r of 1, and then it's going to deplete to some value of r of z. I guess we could put z equals d out there. And s is going to go from 0 up to some value s of z equals d. Okay, so that's for the transmission case. And for the reflection case, we have, again, we'll consider this an unslanted grating here. So here we have, again, z equals 0 and z equals d. And in this case, we come in with a value of r of z at 0. Here we may have a little bit of something left over, so here we have an r of z equals d again. But the diffracted field is going to be at the entering surface, really. So here we have s of z equals 0 is what we're going to want to derive. The r, again, in this case, we know what the r value is coming in initially. It has some, say, normalized unit amplitude, which we can scale accordingly if necessary. And then it has some value of r of z equals d at the output face, whereas the 0 and d, whereas the signal or the diffracted field is 0 at the back end and has some magnitude s of z equals 0 at the front end. Okay, so we have what we'll say is a set of mixed boundary conditions for this. All right, for the reflection hologram. So the reflection hologram is a little more complicated than the transmission grating. We did, last time we did solve the boundary conditions for the transmission grating. Again, so we had r of 0 equals 1, and so this equals r1 plus r2, and we also know that s of 0 is equal to 0, and this was s1 plus, s2. And so with that, we were able to find a solution for s of d, the amplitude. So this is our field amplitude at z equals d, and that was equal to j times the coupling coefficient over c sub s. Again, that's the cosine of the diffracted beam angle inside the medium again, times gamma 1 minus gamma 2, those big long expressions that we have here. By the way, this is the plus is for 1 and the minus is for 2 in that. So we have that times e to the gamma 2d minus e to the gamma 1d. All right, so that's the field amplitude that we have, and then from that we can get the diffraction efficiency. So if you missed the last lecture, you kind of got caught up at this point, okay? So, and again, this is, I think it's a good way to begin, give a little synopsis of what the main points were that you need to retain from that lecture. All right, so now, looking at some new stuff now, what we didn't do is solve for the reflection hologram or reflection grating. And so we have a different set of boundary conditions, right? And so we have here, first off, since the beam is coming back in a negative z direction, right? Cosine of theta sub s is in the relative to the z-axis. So again, this is our z-axis. So the cosine is negative. So we're in that second quadrant there, or the third quadrant, and c sub s is less than 0. All right, and so r and s travel in opposite directions is really what that is telling us, okay? Which is the nature of the reflection hologram. So here we have that our boundary conditions, we have r of 0 equals 1, and we have s of z equals d equal to 0. On the back end here, we don't have any amplitude, because there's nothing propagating in that direction from that reflected beam. All of the reflection is coming out into the incident region. All right, and so this now constitutes as you can see here, one set of boundary conditions is defined on one surface, z equals 0. The other field boundary conditions are set on the other surface, z equals d. So we have a form of mixed boundary conditions that we have to contend with. All right, so actually, for my part of my dissertation work, what I had done was I had the same situation, but I was looking at multiplex volume holograms for reflection, and so I had to solve this particular problem for mixed boundary conditions with multiple gratings, and so that became it had a whole set of coupled wave equations, not just two, to solve, but there's some techniques using these Runge-Kutta algorithms where you can use those to solve it and do kind of a shooting approximation, which actually converged very nicely and predicted the result very nicely as well. So even though these are mixed boundary conditions, they're not insurmountable as far as solutions go. Okay, so again, so we have r of 0 equals 1. So what this tells us is that we have, once again, r1 plus r2 is equal to 1, all right? Because, again, here we have z equals 0, and these fields that we have, that sets these two exponentials equal to 1, and so you're just left with the r1 and r2. So that's where that comes from. And but now for the other boundary at z equals d, we have s1 e to the gamma 1d plus s2 e to the gamma 2d equals 0. So we can't get by with dropping those exponentials out in this case. All right? So we have this equation to work with. So let's kind of play around with that a little bit. And so first thing we'll do is we'll create one equation from this. And what we'll do is to add a term which is s1 e to the gamma 2 d to both sides, all right? So we end up then with S1, and again, we can put that over there and then add this term to both sides. So we have S1 times e to the gamma 2d minus e to the gamma 1d is equal to S1 plus S2 times e to the gamma 2d, okay? So and all we've done is add this term to both sides. The next thing that we'll do is we'll subtract the following. We'll subtract S2 e to the gamma 1d, the opposite, to both sides. And in that case, we have S2 times e to the gamma 2d minus e to the gamma 1d equals minus S1 plus S2 e to the gamma 1d. Okay? So these are all constants. And what we're really after is this, right? Because that is going to tell us S of z equals 0 is going to be equal to S1 plus S2. So that's what we need, is that term right there. All right, so what we've done there is kind of construct a couple of equations that have that term in it. Okay, and so for instance, now we can write S1 or S2 in the following way. We can say S1 is equal to what we need, which is S1 plus S2, the sum of those two, times e to the gamma 2d divided by e to the gamma 2d minus e to the gamma 1d. And similarly for S2, okay? All right, so now if we take our coupled wave equation that we had, so if we take the equation c sub s gamma sub I plus alpha plus j times the detuning parameter. So we have that, and we multiply it by si, either S1 or S2. That's equal to minus j kappa Ri, all right? And if we can do that for, say, both of those terms, we then have j times, and we add them together, j times kappa R1 plus R2, right? But that's just equal to minus, sorry, there should be a minus there, minus j kappa, right? Because R1 plus R2, again, this is at z equals 0, all right? And so R1 plus R2 is just equal to 1. And this then is equal to S1 plus S2 times alpha plus j times the detuning parameter plus c sub s times gamma 1 S1 plus gamma 2 S2. So by just kind of playing around with this a little bit, we actually have it in a form that we need, because all we have to do now is substitute in this form here for S1 and the same form for S2, and we got it, right? Because this is S of 0, and we can then just solve for S, and each of these has that factor in it. And so from that, we end up with, again, so S of 0 is just going to be equal to S1 plus S2, and that is going to be equal to minus j kappa, right? So we divide everything. We're going to have a S1 plus S2 in both of these, factor it out, and then divide it out. So we have minus jk over alpha plus j times the tuning parameter plus c sub s, and then we end up with gamma 1 e to the gamma 2d minus gamma 2 e to the gamma 1d over e to the gamma 2d minus e to the gamma 1d. So it's a little messy, but manageable. All right. So again, so we had this for the transmission case, and we have this here for the reflection case. And this is kind of the general solution for a transmission and reflection hologram. Note, too, that we have these pretty messy gamma factors that we also have to deal with, because they have in it the nature of the hologram, right? By that I mean that we have if there's absorption involved, if there is so we don't want to forget that last part. So we have absorption, we have the modulation, which could either be the phase modulation or the absorption modulation, and we also have the detuning. So by kind of breaking this particular term down, we can now look at different types of gratings that we would most likely come across in working with this, in working with doing some holography. All right. So what we found though was S, right? And so this is the field amplitude. Okay. And by the way, since we've defined all of this in terms of the fields, the alphas that we have here are also amplitude absorption, not intensity absorption, which makes a difference. There's a factor of 2 in what you have for the absorption term. So, and that comes up frequently when you're doing this. I don't know if it shows up in the homework or not, but in practice it shows up all the time. Okay, so the point I was trying to make though is that now we still need the diffraction efficiency for the hologram, and so for that we have our efficiency again is going to be now equal to, it's the ratio of, or so we have S times S star, be it either for the transmission or the reflection case, and we have to put this obliquity term in here, which is C sub S magnitude, because C sub S could be plus or minus, and the efficiency can only be plus, all right, divided by C sub R, all right. And so, again, what this particular term is there for is because, we're coming in at a interface with this beam, and so the power that we have is going to be projected, say, along that surface, and so we need to account for that in some way. We're spreading that out from here to there, so we have to account for that with that obliquity term. Okay, so now, again, so we've basically solved the problem for transmission and reflection cases, and so now we want to look at a couple of different specific cases, both for the transmission and the reflection case. And this is really where the power of this approximate coupled wave model comes into play, because it allows us to kind of come up with some very intuitive expressions that we could work with and even memorize almost, and use them whenever we have the need to evaluate the problems. Okay, so again, if we have our transmission, let's first do the transmission case. And so let's rewrite this. So we have S sub D is going to be the amplitude term that we need. And so now let's add some of those terms into those gamma 1, gamma 2 that are specific for the transmission case. All right. So we want to add in gamma 1 and gamma 2 that are specific for this condition. And so for, again, this is for a general transmission hologram still. We can write this as minus J C sub R over C sub S to the 1/2, an exponential of minus alpha, where alpha is the average absorption, times d over c sub r. And then we have another exponential e to the chi here, which I'll define in a minute. And then we have sine of nu squared, which I'll define in another minute, eta squared over, all this is to the 1/2. That divided by 1 minus chi squared over eta squared, also to the 1/2. All right, so that's putting in some of these values for gamma. And so the nu that we have here, this is sometimes referred to as a grating strength parameter because it has in it the factors that increase the diffraction efficiency of the grating, which are the coupling coefficient and the thickness, divided by these cosine factors, c sub r, c sub s. We take the square root of the product of those two. So this, again, this is, we'll see this over and over again. So this is kind of a grating strength, and as you can see, it has in it the factors that will increase the overall efficiency of that grating. Now, this other factor, this chi, this is kind of the loss and detuning term. All right, and so here this is equal to 1/2 d times alpha over c sub r minus alpha over c sub s minus j times the tuning parameter over c sub s. So as this little label tells us, we have in it the losses and the detuning that are going to affect the performance of that hologram. All right. So again, this is kind of a, I should qualify this as a general transmission hologram. And again, all we've done is kind of incorporate the gamma 1, gamma 2 terms that are kind of relevant here and kind of group them a little bit more in a little more easier way to see, okay, to see where things are going. So now let's look at some specific cases of the transmission holograms. So first case, probably the most important case, is the phase transmission hologram. And I say that because 99% of the time, what you're trying to do is to try to make the most efficient hologram you can, and the way to do that is to make a phase hologram. All right, and so for a phase transmission hologram, we have, or we would like, alpha and alpha 1 to be equal to 0, right? Alpha 1 is the modulation of the absorption, and alpha is the average absorption that we would have. All right? So with that, we end up with just kappa is now just equal to pi times the refractive index modulation over lambda. All right? Okay, so we now, so you can see here, these terms are going to drop out over here, you know, and then a couple of things will change. This term here is going to go to 1 and so forth. So things are going to simplify. And so plugging those in, we end up with S of D again is just equal to minus J, C sub R over C sub S. So that part didn't change. E to the minus J chi. Now, I'm following Kogelnick's notation here. So those of you very sharp here are seeing that this was chi, and now we have a minus j in there. Well, the reason we have a minus j, I'll explain in a minute. Let me write the rest of it, because some other things change too, and I'll be able to hit those as well. And then we have sine of nu squared plus chi squared. So notice here it was a minus, and now it's a plus. Why did that happen? Well, we'll see. Over 1 plus chi squared over nu squared to the 1/2. So why did some of these signs change? Well, the signs change because we have parameters. Well, the new parameter stays pretty much the same. Nu is pi n1d over lambda CRCS, so that's just to the 1/2. That's just this one written out. But the chi parameter is now just equal to the detuning parameter d over 2CS. All right, so here, notice there was a j in here. So rather than keep the j in the chi, if you take it out, you end up with that. And notice we have these chi squares here. So whenever you square j, you end up with a -1. So you have the -1 canceling that negative, and you end up with these positives. Okay, so I didn't screw up again. I just it just comes out of the complex or the imaginary number multiplications. Okay, and so so again, with that, we have that the efficiency now, eta, we can write that as just being equal to, using our definition, C sub s over C sub r SS star. And so this now just works out to be sine squared of nu squared plus chi squared to the 1/2 over 1 plus chi squared over nu squared. Okay, so again, we got rid of these square roots. This is still a square root in the radical, or within the sign, but the sign itself is squared in that case. Okay, so again, we can, so this allows us to detune from the Bragg condition. We could have, a slanted grading or an unslanted grading taken into account there. So it's kind of a general result for evaluating the transmission hologram. All right, so
Is that denominator supposed to be the square root as well?
We have the estimate star.
is it supposed to be square? No, because this one is the square root, so it works out pretty nicely. And by the way, this expression is probably one of the more used forms of the coupled wave model, because again, most of the time you're dealing with transmission, or a lot of times you're dealing with transmission holograms, and in those cases you're usually working at phase holograms. So let's look at some results that we might see for in using this expression. So if we make a little plot here, we can plot the hologram efficiency, and we can have, say, the normalized efficiency as a function of this, basically the tuning parameter. All right, so let's see, we have 1, 2, 3, 5. And so if we can have a couple of different values for nu 0. So if we have this eta is equal to, nu, nu is equal to pi over 4, the efficiency is going to be 50%. If nu is equal to pi over 2, efficiency is going to be 1. And if nu is equal to 3 pi over 4, then nu 0, or eta 0, oh, I'm really losing it, is equal to 0.5. All right, so again, we're going to normalize all these, and what we like to see is what is the bandwidth, what's the selectivity bandwidth of these efficiency values for different gratings, right? Each of these correspond to a different coupling or grating strength for that hologram. So if we have, and so we can normalize, these are all normalized, so we have a value of 1 here for each of these. And so if we have nu over 2, we're going to end up with a value which comes down, actually it comes down here to about reaches the minimum around 2.7, and then it starts to go up like that. So this is for nu equals to pi over 2. And if we have nu equals to pi over 4, then that one's going to kind of come down a little bit broader characteristic here, and then it starts up again more slowly. So here is nu equals pi over 4. And if we have 3 pi over 4, all right, so then we end up with a value that comes down around 2.1. So this is about 3.5. This is about 2.1. And then it has a starts to rise more quickly out here. So here's nu equals 3 pi over 4. Okay, so this so what we're seeing here is a kind of some interesting characteristics. We see that we have a broader curve, right? This again is telling us, you know, this is eta here, or I'm sorry, chi, is going to be, this is related to the delta theta, delta lambda for that grading, right? So what we're seeing is that a more selective characteristic in terms of wavelength and angle for that grading as we start to increase the grading strength, right? Because these are for different values of nu. And so we went from pi over 4, the efficiency is 0.5, then the efficiency goes up to 1, and then as we keep increasing that grading strength, instead of keep increasing, it actually goes down. Because we can kind of see that here. We have this sine squared function in this diffraction efficiency function. And so sine squared is a modulating function, right? And so you can actually over-modulate a transmission grading and start to see its efficiency decrease. But you can still improve, if you need the selectivity, you can actually over-modulate it, decrease your efficiency a bit, and get some higher selectivity. Now, there's a very useful case. So this is, again, for very arbitrary, we could have slanted gratings and so forth. So let's, and also be off Bragg, all right? So let's look at this case of, a special case here where we're at the Bragg condition. All right, and so we have the tuning parameters equal to 0, which in turn implies that this chi is equal to 0, all right? Okay, so is that chi or is that eta? I forget. I'm losing it right now with my Greek symbols. I know that's nu. I'm pretty sure that's eta, right? And so that must be chi. We'll call it chi. Psi. I think that's psi. I think chi is this one, right? So that's psi. There's a little s in there. Oh, like that? That's psi. This one is chsi or something like. It's kind of pronounced like that. Psi. It's a little hard for me to pronounce with my New Jersey upbringing. But anyhow, all right. So if we have the Bragg condition, so we have no detuning, and in addition, let's make this a unslanted grading. And so what that does is when we have an unslanted grading, again, in the transmission case, the fringes are along the z-axis and the k vector is along the x-axis, right? So in that case, we have c sub r equals c sub s equals themselves, and so we can just call that cosine of, say, theta 0, all right? And so in that situation, the efficiency that we have here, again, so this is 0, so that goes away, that's 0, so that goes away. So we're just left with this nu squared in the sine. And when that happens, we end up with eta is then just equal to sine squared of the grading strength parameter, pi n1d over lambda, and we have square root of CR times CS, but CR equals CS, and so we just have one of those, or as noted here, cosine theta 0. Okay, so this is a very easy function to remember, and I'd like you to memorize it if you can. Very handy to do. And so with that, we can now see very clearly this modulation and overmodulation effect that we would have. So here, if we plot the grading strength parameter, pi n1d over lambda cos theta 0, we have, for the diffracted field, we're going to start out here. Again, this is our efficiency, maximum value of 1. So the efficiency is going to have a sine squared function. So it's sine squared, reaches 1, comes back down to 0, goes back up, and keeps doing this, right? If you have, as long as you have a nice linearly increasing function of n1, right? So if this is n1 with, say, exposure that you have, you can get this, all right? And you can actually get pretty close to that. Yeah?
So theta naught is the initial construction angle inside the medium, correct?
Yes, that's the Bragg angle inside medium. And remember, we were somewhere back here. Anyway, somewhere back there I had defined that theta so we have theta equals theta 0 plus delta theta and so forth. So this was if we had, say, cosine of theta, which was equal to C sub r, might have this value. But now we're just saying that we're at the Bragg condition, so that delta theta is equal to 0. Okay? And the detuning parameter, in turn, is equal to 0.
One more quick question with N1. If we have a material that is changed index, let's say after processing, which atom would you then use?
Okay. So that's a good question. So what that means a couple of things. We haven't really talked about that yet, but that is, since this is the angle inside the medium, right? And this is the angle or the wavelength, the free space wavelength, all right? So when we have an average change in the refractive index, we're actually going to create a detuning effect, okay? So I'll talk a little bit more about that. You'll experience that all the time, because most materials will have some average refractive index change. So there's two ways that, so not only that, so generally when you have a grading, all right, if it is slanted, if it is not unslanted, you're going to have this problem. So here's, again, x and z. So if now prior to exposure you have index n, and then after exposure you have index n prime, that will change the Bragg angle, okay? Also what happens is this thickness is either going to shrink or swell, and that's going to tend to rotate or change the grading vector. Actually, we're experiencing this now, and I was going to explain to my students how to determine what those effects are. Maybe I'll explain that to you, or give a little summary of that too, because there's actually a couple of interesting things with the Bragg circle that I recently kind of found out, which I'd like to share with you guys too. So, because it kind of dictates how to design holograms better. But maybe let me finish this first, and then we can go over that. But that's a very good question, because there are going to be these factors. This assumes a very ideal material, doesn't shrink or swell, doesn't change refractive index. But that being aside, all that's going to do, again, since you still can get, Bragg matching, with our, Bragg circle, all that will mean is that you're going to have to change either the wavelength or the angle a little bit, and then you can peak the efficiency again. So the reconstruction conditions are going to shift again from your construction conditions. Okay, but this is a very important result, and the peak occurs right when all of this n1d over lambda cos theta 0 is equal to m times 1/2, where m is an integer, right? Or an odd, sort of an odd integer. Yeah, it's an odd integer. All right, so here, so when this is 1, you'll have a peak, this first peak. So this then is pi over 2, right, because you have a pi in there. And then this second peak occurs when this is 3 pi over 2. All right, and then similarly, a lot of times you might also want the reference beam. So that is going to have the complement of that. So the reference beam R is going to reach a minimum at pi over 2 and then peak up again where although I kind of displaced that, where that signal beam is a minimum, okay? So the two waves again, that really shows the coupling, right? So you go from one that has very high efficiency to the other one has minimum efficiency and vice versa. Okay, so that is, kind of an ideal phase material, but, that's kind of rare to find a material that will really satisfy or have those particular conditions. So what you usually end up with is a grating that has some loss in it, okay? So the next case that let's look at here for the transmission case is we'll look at a lossy transmission hologram. All right, and so in this case, we we have that alpha 0 now is the average absorption is no longer 0, but we're not going to assume any absorption modulation, which may not be really that good of an assumption, because usually if you have some absorption, you might get some absorption if the material's responding in absorption, okay? And then we have our coupling coefficient is still primarily going to be a refractive index modulation, all right? So with this, remember we talked about the propagation constant in the Helmholtz equation at the start. The k squared is beta squared minus 2j alpha beta. So in the last case, this term was not there, but in this case, we have to deal with it. And here we have 2 kappa beta times e to the j k dot r plus e to the minus j k dot r. Okay? So again, we can go back to that general form for the transmission hologram here and modify it, okay, with these parameters that we have here going into that gamma 1, gamma 2, and we end up with a diffraction efficiency here, which is equal to now simply a absorption term exponential minus 2 alpha d over c sub r, and then e to the 2 psi sine squared of nu squared minus psi squared to the 1/2 over 1 minus psi squared over nu squared, where nu is equal to kappa d over CRCS as before, and psi is equal to 1/2 D, and we have to include the absorption, so we have alpha over CR minus alpha over CS, or alpha 0 over CS. That should be a 0 as well. Minus J, the tuning parameter, over C sub S. Okay, so notice it looks pretty similar. You know, it has this same functionality, this modulated functionality that we have, but it also has kind of this average absorption term in it. And as I mentioned too, this, you know, alpha is the amplitude absorption, and so the diffraction efficiency is representing the intensity that's diffracted. So we end up having a factor of 2 there in multiplying that absorption coefficient. Okay, and so lots of materials like, you know, even like silver halide, and even that polymer material, the bare polymer that you guys used in the lab, that has an average absorption. It's not clear when you look at it, even after you know, kind of fix it with some sunlight, it still has some residual density to it, and so it's not truly a phase, strictly just a phase grading, but there's some loss in it. Okay, so the last transmission type hologram we can look at, or distinct hologram that we'd like to look at here, is a absorption transmission grading. It's one that we haven't done yet, or hologram. All right, now in this one, we're going to modulate the absorption and not the refractive index. So N1 now is equal to 0. Kappa is now going to be equal to minus J alpha 1 over 2, if you recall from earlier. And also, since alpha 1 is not 0, then that automatically implies that alpha, or alpha 0, is also not 0. Okay? We have to have some absorption in order to have the absorption modulation. All right? Now, if we just, so to make things a little simpler, let's just consider an unslanted grading here. So we have C sub R equals C sub S equals cosine theta 0. And in that case, we'll end up with a S of D is equal to minus alpha D over CR e to the minus j psi. And here, instead of a sine function, we are going to end up with a hyperbolic sine, a sinh function, because it's an absorption modulation, and we have absorption in the medium. Nu squared minus chi squared, again to the 1/2, divided by 1 minus chi squared over nu squared to the 1/2, where nu, again, is equal to alpha 1 d over 2 cosine theta 0, since they're the same in this case for unslanted. And the psi is equal to the detuning parameter times d over 2 cos of theta 0, which, again, this was equal to, for the approximation form, small deviations from Bragg, delta theta, beta d sine of theta 0, minus 1/2 delta lambda over lambda k d tan of theta 0. Okay, so that's the amplitude, and the efficiency eta here is equal to e to the minus 2 alpha d over cos theta 0. Notice that the average absorption both here and also in this case are alpha, or are d over cosine of theta, which is kind of the effective distance. It's not just the straight through distance. if this is z equals 0, 0 and d, but we actually have to go at some distance here, and here's, say, the angle, theta. So, you know, the absorption is going to depend on that actual optical path length. So we have that times the hyperbolic sinh squared of alpha 1d over 2 cos theta 0. So here, again, we end up with something kind of similar to what we saw for the unslanted phase grating, except the grating strength that we have is with this absorption modulation. And here we have also this average absorption. Now, with this, there is an optimum efficiency, right? Notice here we have two functions. We have a exponential, decaying exponential, and we have this hyperbolic sinh function. So we have the product of those two. So with that, we end up with, so this looks something like this, where this function gives us a decay as a function of the absorption, and the other function, the sinh squared function, gives us an increase. And so we're going to end up with something like that, all right? And the maximum modulation that we can get for alpha 1 is, if this is the average absorption, right, the maximum modulation is just equal to the average absorption. So alpha 1 equal alpha 0 is going to be the maximum. When we put that in to our expression here, we end up with a alpha 1d over cos theta is equal to about 1.1, all right, and that which corresponds to the logarithm of 3, which comes out of this at this peak value here. And so this gives us a diffraction efficiency which is maximum for a volume transmission hologram, which is a whopping 3.7%. Okay, so it's even less than what we were talking about, you know, the thin absorption grating. Remember we were doing the Fourier analysis? That one we found was 6.25%. So the reason for that is it's thin, and so you don't have much average absorption in that thin grating. But for the absorption grating, it has to pass through it, and so you end up with this very low diffraction efficiency. That being said, you can still make very good high fidelity gratings with these absorption gratings, and that was done for a long time with silver halide in making master holograms that have very low scatter that could then be used for copying purposes. Okay, so we can have kind of a mixture as well. So we could have a mixed phase and absorption grating. All right, and so in this case, this will occur both in silver halide and also in some photopolymers. In this case, N1 is not equal to 0, as well as alpha 1 is not equal to 0. And so the coupling coefficient now is kind of the full, and again, we made this an approximate coupling coefficient for an optical medium. So we have pi n1 over lambda minus j alpha 1 over 2 for the coupling coefficient. That gives us a amplitude at the output face of the hologram. S of d is minus j exponential of minus alpha 0 d over cos theta 0 times sine of kappa d over cos theta, where kappa now is a term that includes both absorption and phase modulation. And so the resulting diffraction efficiency has in it sine squared of pi n1d over lambda cos theta 0 plus the absorption modulation, which is a sinh squared alpha 1d over 2 cos theta 0. And we still have this average absorption since, again, the medium has to be absorbing if we have an alpha 1 exponential of minus 2 alpha 0, the average absorption, d over cos theta 0. So depending on how much absorption modulation you're getting, which that's going to dictate this, loss through the hologram will set your efficiency for the grading. So that kind of completes the full range of possibilities that we might have for transmission gratings. And so let's start to look at some of the reflection holograms. All right, so again, so in this case, you know, we have both beams coming out at the z equals 0. So here's our r, and then we're going to have some s of z equals 0 coming out here that we're describing. And so the general form for the reflection grating efficiency is equal to c sub s, magnitude, again, because it's negative and efficiency can't be negative, c sub s over c sub r times kappa squared divided by, we have alpha plus j times the detuning parameter plus c sub s times gamma 1 e to the gamma 2d minus e to the gamma 1d times gamma 2. Sorry, misplaced those. Over e to the gamma 2d minus e to the gamma 1d. All right, so again, so the nature of the grading is going to be dictated by these, by gamma 1 and gamma 2, and that'll tell us whether or not, you know, we have an absorption grading or a phase grading. So let's first look at the phase grading. So we have a phase reflection grading. Again, this is usually the most desirable form of the grading is a phase grading, because once again we'll have very high diffraction efficiency. So kappa is equal to pi n1 over lambda, and we have alpha 1 equals alpha equals 0 for this case. And going through this and plugging in, we end up with the amplitude. Again, this is at z equals 0. So the amplitude now is equal to c sub r over c sub s square root times 1 over j times psi over nu plus 1 minus psi over nu squared, and we have this term here to the 1/2 times the hyperbolic cotangent. It's kind of messy because we have, again, we had all these gammas in here. We're almost there. Nu squared minus chi squared to the 1/2, and all of this is in the denominator, okay? And we have psi is equal to minus the detuning parameter d over 2 cs, and nu is equal to j pi n1 d over lambda square root of cr cs, okay? So for we want the diffraction efficiency, right, we take S times S star, multiply it by CS over CR, and we end up with eta is equal to 1 over 1 plus 1 minus psi over nu quantity squared over the hyperbolic squared square root of nu squared minus psi squared, and all of that is together, and all of that is in the denominator. Okay, and so that still looks pretty messy, so let's look at a couple of simplifications. So one is, if we are at the Bragg condition, that is going to imply that this term is 0. Okay, so that makes things a whole lot neater. And we end up with the efficiency in that case is equal to the sinh squared of nu over hyperbolic squared of nu plus 1. Okay, and all right, if we make it or if we expand this a little bit, we end up now with this is going to be equal to just the hyperbolic tangent squared of j pi n1 d over lambda square root of CRCS. Okay, so this is kind of the reflection grating analog of what we had for the transmission hologram. All right, and so, and if, again, if we have an unslanted grating, then this term just becomes, here, this just becomes cosine of theta 0. So again, so this is at the Bragg condition, and for an unslanted grating, it's just pi n1d over lambda cosine theta, all right, but this one is not a oscillating function, right? This one is a asymptotically increasing function. So the two are a bit different, and we'll talk a little bit more about that next time. Okay, there's another simplification here that pops out too. Since CS is actually negative, right? So we then end up with a j coming out of here, and so that's going to drop that j. So I'll go over that again at the beginning of next lecture. Yeah.
So is the homework due?
No. So we had that come up early in the class, and the homework is going to be due on next Tuesday, not Thursday. Yeah. So I think you can, probably do most of it now, but you can have a couple extra days to work on that. So. Okay, and next week too, we're going to have the lab on Monday and Tuesday. I'll go over the lab. It's a multiplexing experiment. Be multiplexing some gratings and looking at what effects you get when you do that. Okay, all right.